All right, so in this lesson we're going to start looking at electric field calculations. How do we deal with things like a line of charged particles, or a ring of charged particles, or a disk of charged particles, where there's not just 2 or 3 or 4 charges, but instead a distribution of charges. These types of calculations can become much harder because every time you add a point charge, you need to add more stuff. What we can do with something like a distribution of charges is model it as a distribution of number of individual point charges, and then say the electric field is a summation of electric field from each of those individual point charges. Now what we're actually doing here is integration, trying to say we're going to break up, say, a rod into little individual chunks and find the electric field from each of those chunks. So we've got a line, and I'm going to say it has a total charge Q, and it's oriented on the y-axis from y equals negative a to y equals a. And I want to know what is the electric field at point P, located on the x-axis, a distance x away from the origin. So this is very similar to the example problem in the last lesson, except that instead of having just 3 point charges, one at the origin, one at negative a, and one at a, this is a distribution of charge. So what we do is I'm going to model this as a series of point charges. Each one has a charge, which I'm going to call dq. So the density of charge on this line is going to be equal to Q, the total charge of the line, divided by 2a. Now I use lambda here for density. Lambda, if you ever see that used, it generally relates to a linear density of charge. We'll see rho, which would be a volume density of charge, and sigma, which is an area density of charge. And so those are some general tricks that we usually use to find. So what dq really is it's equal to the linear density of charge times how big the little chunk is of charge that I wanted to make. And so I'm going to say that this chunk has a thickness or a length of dy. And so dq, the charge of this little chunk dy, is lambda times dy, or q over 2a times dy. Now where this becomes helpful is when I start to begin to define how I'm going to find the electric field. Probably helpful for me to know what r is. In this case, r is going to be x squared plus y squared square root, where x is the distance between P and the origin, and y is this distance in here. So dE, the electric field caused by that little point, which I have as the blue vector there, is equal to 1 over 4 pi epsilon naught, or k, dq over r squared. Now a few things that I can do at this point is I could substitute what dq looks like, q times dy over 2a, and then substitute what r squared is. Should be x squared plus y squared. And so there's what dE looks like. And what I know should be true with this is if I integrate over the entire rod, because there's as much charge from the origin to a as there is from the origin to negative a, I'm hoping the y components will cancel out. So when we do this process, hopefully the y components are going to cancel. So let's double check that. The y component of this is going to be dE times the sine of that angle theta. I can divide sine of the angle theta by doing opposite over hypotenuse, y over x squared plus y squared square root, which means that the y component of the electric field for this little point is q y dy over 2a x squared plus y squared to the 3/2 times k, essentially, 1 over 4 pi epsilon naught. So if I pull some stuff out and set this up to integrate, I'm going to integrate from y values negative a to a, and I'm going to integrate this function y dy over x squared plus y squared to the 3/2. And if you were to plug that into your calculator, you are going to get 0. It's just going to spit it out for you. And the reason why you're going to get 0 is that y over x squared plus y squared to the 3/2 happens to be an odd function. What that means is if you integrate an odd function from negative a to a, negative infinity to infinity, negative 1 to 1, you always get 0 for an odd function. And the main reason for that is, generally speaking, the integral of an odd function is an even function. So we're not going to worry about doing this integral because I've seen odd function, I know it's 0. So let's go to the x components of things. In this case, I do cosine of theta, which would look like x over square root of x squared plus y squared. And so I get something that looks really similar, except instead of, well, a y on the top, it's really an x on the top. And at this point I get something also really similar. Pull everything out, qx times 8 pi epsilon naught a. And so all of that are all the constants that I pulled out front. And so I get the integral of x squared plus y squared to the 3 halves on the bottom dy. So I need to take the integral of this thing. And that's not necessarily an easy one to take. If you actually look this one up, you get something that looks like this: y over x squared times the square root of x squared plus y squared. And so if we actually work out what that looks like, it should be a minus negative a. And so you end up with 2a x squared times x squared plus a squared square root. Now, the way I actually use this is I actually went and looked at this up in an integral table. And what happens when you actually work out all the math and work out all the algebra is you get this function here. Q over 4 pi epsilon naught times 1 over x times x squared plus a squared in the square root. And that is the electric field at point x at point P in the x direction. Now, a few things to point out. One thing that's really cool is what if you make x really, really big? So what if P is really far away from this rod? What happens if P is really far away is that x squared plus a squared basically becomes x squared. And so you have, on that second one, 1 over x times the square root of x squared. And so you end up with 1 over x squared. What that means is it looks like a point charge at a distance x away from you. Now, another cool thing to think about is what if a is really big compared to x? So what if this line is infinitely long? So what if I'm so close to this line of charge that it looks like it goes forever to the right and to the left? So if we remember that q is, or if lambda is equal to q over 2a, we can actually factor out an a on the square root in the bottom and get something in terms of lambda, the density. If something is really, really long, I might not know what q is, what the total charge is, but I probably know what the linear density of charge is. So when I do that and go to factor out an a, what happens is, if I factor out a squared, I get x squared over a squared plus 1 in here, and I get an a out over there, and that q over a basically becomes lambda. And so you got lambda over 2 pi epsilon naught, or I guess q over 2a, excuse me, equals 1 over x squared a squared. And if a is really, really big, infinitely large, which we said it was, then x squared over a squared basically becomes 0. You get the square root of 0 plus 1, so you get 1 over x. And so that's how you get the lambda over 2 pi epsilon naught x as your value for electric field for a long, long, long straight line. Some of these, like this one, we'll find a different way in a later lesson. Now the next problem that I have is what if we have a ring with a radius a, and I have a point P that's on the x-axis, and the x-axis goes right through the center of the ring, and we want to figure out what is the electric field at point P. Kind of some of the same things happen. We would do dq equals over x squared plus a squared times 1 over 4 pi epsilon naught. Looks like dE. One thing to point out is that only the x components are going to make a difference. All the y and z components will actually cancel themselves out. And so if I go to plug in what the cosine of that thing looks like, here's the cosine of that angle. We plug that in. We get x times dq over that. Well, if we actually integrate that all out, we get something that looks like this. X q over x squared plus a squared to the 3 halves. Now you can do this by finding out how big dq is. It would actually be equal to q divided by 2 pi r, and work it out that way, or 2 pi a, and it actually works itself out the same way that you get the same expression when you go to integrate that. I just didn't set up my integral that way because, well, it's a little hard to set up that, and if we integrate dq, we should get q. Now, one of the cool things about the ring as well is if you put yourself at an infinite distance away from the ring, so x is infinitely large compared to a, this basically becomes x cubed on the bottom. X over x cubed becomes x squared. Same thing if a is really, really, really big compared to x, you essentially get something that, well, looks like what we had before. So let's do a disk of radius r with a uniform charge density lambda, and we're going to do this for point x that's on the center of the disk. We're going to use a similar technique to what we used for the ring. dq in this case is going to be lambda times dA, and dA we're going to look at it as the area of that little ring, which would be 2 pi r dr, where dr is the thickness of the ring. This is the same symmetry as the disk. We can actually use the exact same process and get the same integral. And when we get to this point, we just plug in what dq is and put the limits 0 to r. So what I do at this point is do some simplifying, because there's a lot of things in here that are going to cancel out. The pi's, the 2 and the 4. I can pull an x out, it looks like. And what happens when you simplify it is you get something that looks like this. And interestingly enough, we get something that looks very similar to one of the integrals we had before. And so if we actually go and solve that out, use an integral table, here's the solution that we get. This one happens to be a little bit easier to solve because you can use u substitution to solve that out without an integral table. And what we end up with as our value is this. We actually calculate out the electric field. That we get x lambda, or x sigma over 2 theta times 1 over x minus 1 over x squared plus r squared. Now the cool thing here is if, say, x is really big compared to r, what you end up with is an odd result, and the odd result you end up with is the electric field becomes 0. But if you think about that for a second, if you go infinitely far away from this disk, maybe it would end up being 0. If you think r is being really big compared to x, you end up with sigma over 2 epsilon naught as your result. And so those are important things to kind of keep in mind or keep in your head. Here I've actually kind of worked it out and plugged everything in there. So those are some ways to calculate this out using integration. The one thing I'd point out about calculating electric fields by integration is that lots of times you end up with integrals that are not all that pleasant to work out or not all that pleasant to solve. A lot of times you end up getting integrals which are not very fun to solve or very fun to work out. So what we'll look at in the next set of lessons is a second technique to find electric fields from distribution of charges. And for many of these situations, the second technique works and is actually easier and faster. There are a few situations, like I think the ring, where this second technique doesn't really work all that well. And so you just kind of need to have both tools in your toolbox to work them out. In the case of your integration technique, as long as you can define what a dE is or what a dQ is in terms of the variables you have, you can set up an integral to solve it. There are, of course, some symmetries or some situations which would be very, very, very difficult, but it is mathematically possible to do. When we get into our next set of lessons deal with certain symmetrical systems that have very regular patterns that show up. And so we'll see how that works when we look at our next set of lessons.